Right. Now then, everyone. So yeah, I'm gonna talk about the aerodynamic coupling between SPH and some external aerodynamic influence in the context of aircraft fuel jettison. So to start off, let's look. Are you gonna work? There you go. Let's start off looking at what the fuel jettison process is. So here we have two images of the usual locations that one might perform fuel jettison from, one being close to the wingtip, the other being off what is called a flap track fairing, which is this little assembly to house the track mechanisms for the flap. So the reason that we might need to dump fuel is that usually an aircraft could be overweight, and we want to reduce risk of overstressing the airframe or the landing gear, or if we're landing on a particularly short runway. Those are the main suspects. So at the present, the only real way to certify this system is through flight testing, which is quite expensive and wastes a lot of fuel. So we'd like to be able to simulate this as much as possible to reduce those burdens upon the certification process. So that results in a criteria for us doing the simulation to present enough fidelity so that we can identify whether any fuel contacts the aircraft's surface during this fuel jettison process. It could do so through more complicated recirculation of the aerodynamics when flaps or spoilers are deployed. They create these really complex turbulent flows. Alternatively, if we have an engine failure, we could be yawing enough that fuel impinges the tailplane of the aircraft. So there are our main concerns. We want to be able to understand where the fuel goes in these situations. So in order to do this, we're going to break the simulation domain up into three primary sections. The first is the aerodynamics. The second is the continuous fuel phase immediately out of the fuel pipe. And then the third is the discrete fuel phase. So this is where the fuel has broken up into small droplets that act independently of each other and can be considered discrete rather than continuous. So for the aerodynamics, that's a very well understood field already. We use volume-based meshes and we can get good solutions from that. So we'd like to be able to recycle those if possible. The discrete fuel phase is also quite well understood due to aircraft icing. We already know how to convect droplets with very low computational cost. So that's well understood. What is not well understood in a computationally feasible manner is the continuum. Whilst we could use volume of fluid, that has very high computational requirements, both in terms of simulation time and mesh fidelity, to say the least. So we'd like to look at instead using a single phase SPH model. Being Lagrangian based, it reduces our dependency on the mesh. And then by assuming that the momentum of the air is much greater, significantly greater than the momentum of the fuel, we can ignore the influence that the fuel has upon the aerodynamics, such that we can recycle an aerodynamic solution already used for the aircraft performance. So this produces the system we have here, where we have a need to couple the aerodynamics to the SPH. So that's going to be the focus of this work here. So quickly go over the SPH setup. We're using the base Monahan momentum equation, but doing the delta SPH continuity, laminar viscosity from Morris, pairwise single phase surface tension from Nair and Puschel, and a surface tension level set from Moroni with a Wendland C2 kernel, Cole equation of state, and the Newmark beta time integration. So to look at how we're going to couple to aerodynamics, let's first look at the discrete system, ignoring the continuum. So for this, we do some simulations using this to compare against as to what we gain or lose from the continuum. So in this discrete system, we take our classic aerodynamic drag force, and in this we have some explicit stuff where we have the relative velocity between the particle and the cell, where C is the cell and U is the particle. But in this we have coefficient of drag, which is a bit of an unknown, and so for this we create a relationship based on the Reynolds of the droplet, and so that is coupled between them. I'm not going to go into detail of how we integrate for the discrete system. That I would point you to this paper. But for the continuum, how we look at bridging that gap from the discrete droplet is through a neighborhood, an interpolation based upon the neighborhood. So again, to reiterate, we have our drag relationship, and we're going to interpolate the coefficient of drag and the area from that of a sphere, as we showed previously, to some plate continuum relationship. In the Gisler model that was originally presented, the coefficient of drag for the continuum is simply a constant coefficient of 1, and then the plate is your initial spacing squared, is the area. They then feature an occlusion factor based off the angle between the nearest neighbor that blocks some of that force if a particle is hidden by other fluid, such that surface downwind doesn't really see a force. So that's the original Gisler model. We then look to extend that and take a different approach to the continuum representation, but we do keep that interpolation. So instead we look at the pressure that would be induced upon the surface of the fluid, such that the force on a continuum is the normal times a pressure force, and which can be broken into the non-dimensional coefficient of pressure. And then this coefficient of pressure has some relationship that's interpolated again based on the curvature of that surface. So we can get some estimate based on the local geometry as to what the pressure should be. So if we have a bowl, we'll have, and we use 3 primary shapes, being a bowl, a flat plate, and then a sphere. And these graphically are shown here. So we have, for a bowl, a sphere, we have quite a low pressure possible, so they can really suck and break fluid apart. But then we go towards a bowl where we have large regions of stagnation if it's facing the aerodynamic flow. But then if it's facing away, we just have a completely separated stagnant region. So we can get some tuning in here potentially as well moving forward. So to look at the results using these, we have the sphere plate compared against the induced pressure on the right versus some higher fidelity simulation from volume of fluid and an experimental result. So we see that the sphere plate matches the overall movement of the jet quite nicely, but is limited in its breakup capacity due to that lower fidelity representation of the continuum that struggles to create any form of breakup. But we do see that all 3 simulations are resolution limited in terms of modeling these fine droplets that we see in the experiment. All 3 fail to capture that. So moving to a more coupled case, this is where the induced pressure really shines through. The sphere plate shows virtually no breakup in the aligned jet cases. So here, both the velocity of the jet and the air around it are the same direction. And so the occlusion factor, when considered here, really limits the amount of breakup that we can experience with that representation. Whereas the induced pressure model, while still not fully representing the level of coupling observed by volume of fluid, does manage to represent that to some lesser degree due to the instabilities able to be formed through the normal pressure forces. Two dimensions also does play a factor here in that the pressure can't offload around a circular jet column, and we see that large pressure regions can build, causing the strong coupling observed in volume of fluid. So to look at cases more relevant to the fuel jettison system, here we have vortex lattice method. So this is a way of representing wing influence without needing full volume mesh. We simply mesh the surface and we can interrogate that to provide an aerodynamic influence. So here we have the sphere plate model again, and we don't see much breakup at all. And that's because we're quite close to the co-flowing jet case with just some slightly extra aerodynamics on top. So we don't see a great difference from that. But then if we look at the induced pressure model, we do see much greater breakup. We see something much more plausible to what we might anticipate in real life. And we see that some wavelengths are formed in the jet that are most likely related to the resolution of the SPH. So as much as we would like to analyze that, that's most likely what we'll observe. But it still breaks up reasonably rapidly into ligaments and droplets within a few chords downstream, which is a much more positive, much more realistic result. So to look against a higher fidelity method in the use case, we have here a simple three-dimensional wing called the Aero M6. And here we have the SPH using the induced pressure model versus volume of fluid. And here we really see how the mesh-based method can provide limitations in terms of diffusiveness. And we see that the fuel representation just dissipates away. This point is a region where I've increased the refinement of the mesh beyond what would normally be necessary for the aerodynamics. And as soon as it hits the unrefinement, we see that it dissipates almost straight away, indicating how much resolution is required to represent a free surface. Whereas using a Lagrangian-based method, we see that the fuel phase definition is preserved very nicely, and we have good agreement still, even with that. So this really reinforces that a particle-based method is certainly attractive for this sort of simulation. And we're not losing any real accuracy here. So to look at what we might gain from the continuum, in black we have particle tracking simulations that are discrete. So they don't consider the continuum, versus in blue is the continuum SPH model. And this also compares geometries. So on the left, we have an engine nacelle visible in the bottom left versus without. We see that in both cases, there is a difference between the two simulations, but there is a more pronounced variation when the engine nacelle is included due to the vortex interactions off of that nacelle, causing a bit more of a sharper velocity change there. This emphasizes that the continuum is important to the initial breakup and flow direction of the fuel jet. So we are gaining something by doing this extra work. But of course, once we get a bit downstream, modeling the continuum is a bit unnecessary. So in future, we would like to look at transitioning to the particle tracking and saving us even further computation. Again, the final result I have to present is a look at how the particle diameter affects our result. So in blue, we have the same diameter shown previously, which I think was 250 micron particles. And then in blue is 10 micron particles, both using discrete particle tracking. And this simply shows that the fuel direction will depend upon the particle size. So mesh, like resolution independency, is another region to investigate. As much as we have criteria for it, it's obviously computationally bounding as to how much we can investigate that. But this does provide an interesting new avenue to explore as to exactly how much that factors in. So, in conclusion, for simple geometries such as uniform flow, the two-directional coupling, so the fuel impacting the air flow, can be quite important, certainly in the aligned flow cases, as to the specific breakup, but the gross flow is generally quite similar. So you can predict quite well where the majority of the fuel will go. But then used in higher momentum flows, such as the Fuel Jettison case, we see that the agreement matches closer when we ignore that coupling to the first phase, as we get better agreement. We see much better representation with the induced pressure model versus the sphere plate model, but we still need to do further data analysis to more conclusively say that. And then it's difficult to model the jet spray due to the resolution and computational demands, but we do have some preliminary evidence that we are dependent upon that resolution as to what breakup and motion you will observe. And yes, we see it differing from the discrete system, so modeling the continuum does provide a benefit, and you can't simply ignore it without losing some further information. So that's everything. Thank you. And any questions?
Okay, thanks, James. Yes, Stephen, you've got your hand up. Do you want to?
Yeah, so it's really interesting stuff. So the VOF model, when you talk about it being strongly coupled, you're talking about the fact that it's obviously VOF is capturing the interface between air and fluid, and that's kind of the coupling that you're referring to. Is that right?
Yes. So yeah. In the two-directional coupling, it would be, as VOF is that the fuel is changing the air solution, and then vice versa. Obviously, the air is changing the fuel.
Yeah.
So that's where we're talking about a fully coupled, but in this instance, it's also further coupled, being two dimensions, in that if you're representing an infinite sheet that can't break, you get a pressure, like a pressure vortex of air on one side that then just forces the fuel down with no way to offload. So there's this increased coupling in terms of the fuel oscillation, as you see it flipping very, very severely because of two dimensions.
Sure. Okay. But so just to be clear for my own sort of sanity, you're solving both phases using the same finite volume approach.
Yes.
For the VOF, yeah. Okay, so my question then is, I've done some droplet dynamics stuff myself in the past using OpenPhone's VOF capability, and the conclusion I've reached every time is that it's absolutely necessary to sort of bring mesh refinement into play, which is quite difficult to do through the current OpenPhone framework into foam, assumably. Now, of course, we know it's quite similarly difficult with most SPH codes. And my understanding of kind of the capabilities of the code that you have at Bristol, which I assume is what you're using here, is that it won't have that capability as well. So how much of an effect do you think having a variable resolution, both in terms of the mesh-based approach and the particle-based approach, has on the ability to capture the droplet dynamics?
Yeah, like you've exactly hit the nail on the head with what I was, were I to continue this work, that's what almost the first thing I would try and do, because I found a paper, I think last year, where they've looked at particle refinement on the surface for SPH, which is exactly what we would want in adapting the surface. And we have criteria of when to split the particle from like breakup models. So you can probably do that in SPH, whether the computational demands are, but the research has been done. And for free surface interface like flows, adaptive refinement is almost a necessity, really, if you want to get good results, because the mesh or like the resolution requirements to model the free surface is an order of magnitude above what you would need to model, represent any vortex or like pressure information, simply just in terms of representing that defined surface. So yeah, I think it is an important thing, and obviously in OpenFOAM, say in this case that's 2 dimensions, so I can't use the adaptive refinement. It's only valid for 3D and in hexahedral cells. So yeah.
Yeah. Okay. Thank you.
Okay. Yeah, I've got a question actually. With the coupling of the CFD to SPH, do I understand it correctly that it's a one-way coupling where the aerodynamic pressure exerts a force on the SPH particles, but there's no interaction the other way? Is that correct?
Yes. The aerodynamics is not being altered by the SPH.
Okay. And then second question on this slide actually. So with the induced pressure model, you get a breakup, whereas with the sphere plate model, you don't see any effect. So can you explain why an instability develops with the induced pressure model and not with the sphere plate? What's the fundamental difference?
Fundamentally, the difference is in what direction is the force acting. So for the sphere plate, the force is only acting along the relative velocity vector, which in this case is from left to right, almost exactly, because both the jet and the fluid, the air, are in the same direction. And then coupled on top of that is the occlusion factor in this formulation, which reduces a force up until the point of 0, where you have a particle exactly in front of it on the relative velocity vector, so they experience almost no force. It's not quite 0, but it's next to 0. Whereas with the induced pressure, the force is acting normal to the surface. Skin friction is also estimated off of just boundary layer methods. And so you can get, you can get this instability formed, and then you can get surface presented more so to the flow, as would be anticipated in a fully coupled simulation or environment, such that you can start to get viscous effects and more coupling and momentum effects occurring that lead to the breakup.
Okay, thank you. I don't see any other questions in the QA or in the chat. Okay, so